finding the inverse. And this should be a straightforward problem, right? Let's see. So let's assume that there actually is an inverse for this matrix. And let us proceed as we usually do when we would like to find an inverse of a matrix. And that is by augmenting / appending / gluing the identity matrix, which is ones on the diagonal and zeros everywhere else, to our original matrix. And then we proceed with the goal of turning this left-hand side into the identity matrix. So it's kind of like we take this and we put it there, but this will inflict some changes here. This is what we'll see right now. So we proceed with some row operations. If I want to make this with ones and zeros everywhere else, then I will do this column by column. I'll start with the first column. Oh, this is a 0. I can't really make a 0 become a 1 here. There's no such multiple, at least. But I can do something that's very nice. I can switch the placing of the equations like this. So switching rows is fine, because rows just have data about equations, and so there's not really an issue if I do like I just did. But keep in mind, you need to switch everything. So the left-hand side gets switched, but also the right-hand side. And now we have this, weird ones on the diagonal, but they're like this, and that's not so nice. But anyway, we don't care about the niceness of it. We want to have a 1 here and zeros everywhere else. To have the 1 here, I will multiply by half. And then here's what I get. Let's try to be quick. This becomes a quarter. Becomes a half. So the whole row gets multiplied by half. This is my result. Now I can start to make zeros. In just a moment, I'm going to go fetch my nice draft. Here it is. So this is my nice draft. I always like to use it whenever I'm doing Gaussian elimination. It helps me focus on what is important, because the most difficult thing about Gaussian elimination is really just the number of steps you need to take. The steps are usually simple, but they're usually multiple of them, and this is not so pleasant. So I would like to use this in a moment, but for now I want to make this a 0. Then I will multiply this row by a -1, so that this becomes a -1, and then I can eliminate this 1. I do this. Let's see what I get. So this is my draft. I have to deal with 6 values. That's not so pleasant. But let me explain how the draft works. So I have this, the row. I multiply by -1. So I get -1 minus quarter minus half, 0, 0 minus half. And then I add it to this other row. Here, naturally, I'll get a 0 by design, And then here I just get minus quarter plus 0. Here this is minus half plus 1. So this is just a half. This is 0. This is 1. And this is minus half. So these are my new values in the new second row that I'll be writing down. Perhaps I shouldn't write this as A, because this does not really signify the matrix A. And then I copy this exact same setup and paste it. I'm surprised we actually still have space. Yes. So I need to update this row with my new values. That's 0. I'll just write them. 0, minus fourth, half, 0, 1, and minus half. Then I would like to do the same thing, by the way, for the other row, but I don't need to because it is already 0. So I don't need to make this 0 a 0. It's already a 0. So that is a good thing. This was the original 0 we had here. So I'm happy about this. I don't need to make zeros of any sort. And that is amazing. And then I have a 1 here and zeros everywhere else. Perhaps it is now a good idea to proceed similarly and try to now get our second 1 on the diagonal. So let's try to do that. How would I do that? The first thing I would do is I would multiply this row by a negative quarter, because then I can, when I do this, there's no running away from it. I need more space. When I do this, this is going to happen. This minus quarter, when I multiply it by, well, not by minus a quarter, I need to multiply by minus 4. That was a really bad mistake from my side. When I multiply by minus 4, I get a 1 here, because minus 4 is the multiplicative and additive inverse of minus quarter. I do the same for the other ones. I get a minus 2 here. Here this remains 0. This is minus 4. And this is 2. And now my goal is to make this entry 0 and make that entry 0. The way I would do this is I would multiply my second row by a negative quarter so that the 1 cancels out with the quarter. Here I would apply the same logic and multiply by a negative half. And multiply the 1 by a negative half so that it cancels out with the minus half. I hope that is clear. Now I will take my values and use them up here so that we're able to avoid mistakes as much as we can. This is our original row. And it will become a new row when we multiply it by a quarter. This will remain as 0. This will become a negative quarter as expected. This will be a half. This will be 0. This will be 1. And this will be, I think it will be a negative half. Then I added to this row. Remember I was adding it to the upper row. So I do like this. Put this here. And now I just need to add values. This remains as 1, because 0 plus 1 is 1. This is now 0 by design. I've chosen this very specific negative quarter so that it cancels out in the end. Now half and a half is, it's not a quarter. This is 0, this is 1, and this is 0. I'm happy because we have ones and zeros. I think ones and zeros are more comfortable to see than fractions. So I'm happy about this. Perhaps I will copy this matrix. Now we were going to change the values that are here, change the values that are there. The new values are 1, 0, 1, 0, 1, 0. 1, 0, 1, 0, 1, 0. Now I just need to do this and multiply by negative half. So I'll use a cool trick. I mean, this was multiplied by negative quarter. So if you want to go from a negative quarter to a negative half, you just multiply everything by 2. Right. You could, of course, check this. I mean, minus half, minus half, minus half, minus half, minus half. Now I need to add to the other row, which is, it's not this one, it's the lower one. And then I add the values. Of course, I'm doing this at a fairly slow speed. You don't need to do this. And you don't even need to use this draft. If you know that you can do it in your mind very quickly, then this is great. But I mean, this is a tutorial and you're probably here because you need to learn something. I don't think it would help you much if I were to just do this in my mind. So please bear with me. This is 0. This is again 0 by design. This is half, 1, 2, minus 1. Good. Then we're very close to our declared goal of making ones here and zeros everywhere else. Let's proceed with the final step, which is to make this half a 1. So I would multiply by 2. This will give me a 1 here, 2 here, 4 here, minus 2 here. And now I just proceed like I did earlier. If I want to make a 0 here, I need to multiply by 2. To multiply this 1 by 2, and then it will cancel out the minus 2. Similarly here, I'll multiply by minus 1 to eliminate the 1. So we just need to do this one more time. I'm happy because with these zeros, this part is really not going to get affected, because 0 times anything will always be 0. And then whatever you add here, you'll just get the same thing. That's also not a bad note. Now let's perhaps multiply by 2. And then this will be 2, 4, 8, minus 4. I want to add this to this row. I get 0, 1, 0. Remember, we designed it to be like this. And now 4 plus 0 is 4. This is 4. And this is a minus 2. So here are our new values once again. So it is a lengthy process, I will tell you this. It's quite a lengthy process. You said 0, 1, 0, 4, 4, and minus 2. Now one more time. We multiply by minus 1. Oh, remember, this stays the same. Now I'm adding this to this upper row, 1, 0, 1, 0, 1, 0, cool row. And now I will update it with the new values, which will remain the same for the part that's, with the dashed part. This is again 0 by design, and now I get minus 2, and minus 3, and 2. This is minus 2, minus 3, and 2. And then, in this case, this should be the answer. On the right, we should have our answer. On the left, we have constructed our matrix of ones and zeros. We've constructed our identity matrix. And because this was successful on the left-hand side, then this should be the answer. Now, let's do our due diligence. We know that if this is A inverse, then in that case, we would have the following, and that is A times A inverse should be equal to the identity matrix. This should always hold. If this were to be the inverse as we claim here. So let's do our due diligence and perhaps multiply this A inverse by our original matrix A. I hope you still remember how to proceed with matrix multiplication. So matrix multiplication is roughly, if you want to talk about it in an algorithmic sense, it's something like an array that stores the dot products between the rows and the columns. For example, this is the row. I take the dot product of the row with the column. It looks like I might need a little bit more space. No, I think it'll be fine. Yeah, so this is, and the place where we stored this dot product is where the row and the column intersect. So you see, if we intersect the row and the column, we get the uppermost left entry. So we do this for all the entries. This should give us the identity. And now I say it should. I don't know what exactly it will give us. This will be the second entry. This will be the third entry. Of course, with the I honestly don't feel bad for you if you play me on 2x. Because I can imagine this is a nightmare to watch. But if you're still here, I'm happy. I'm happy that you are. So I do this. I proceed similarly for all the column entries. So this at least tells you how the distribution of the values in the matrix looks like. If you have at least a basic intuitive understanding of this, then I think it would really help you more than hurt your chances of learning something. And then we do the same thing for the rows. So because this is the second row, it is stored in the second row, in the new matrix, with the dot product. Finally, do this once again. Now, we should get the identity matrix, which means that this should be 1, this should be 1, and this should be 1. We should have zeros on the diagonals. So zeros everywhere else. Perhaps we'll do it very quickly. So minus 2 times 0, minus 3 times 1 is minus 3, and 2 times 2 is 4. So minus 3 plus 4, that's 1. Minus 2 times a half is minus 1. Minus 3 times 0 is 0. And 2 times a half is 1. So this is actually 0. I'm happy. Let's do this again. Because the dot product is you multiply component-wise and then you add the results, just for as a refresher. Now I do the same thing here, so I get 1. Here I get minus 3, so that's now 1 minus 3 is 2. And now plus 2, 1 minus 3 is minus 2, and now I add the 2 times 1 here, I get another 0. I'm enjoying this. This is 0, this is 4, and this is minus 4, so I get 0 here. This is 2, this is 0, and this is minus 1. So this actually gives me 2 minus 1, which is 1. And I keep playing this game, and I get 4 times the negative half is minus 2. This is minus 2 also as well, and this is 4. So it does give me 0. This is 0, this is 4, and this is minus 4. So you get 0 again. This is 1. This is 0, and this is a minus 1. So the minus 1 cancels out with the 1. I hope I'm not making any mistakes here. This is minus 1, and this is 4, and this is minus 2. So I do get a 1 here. So that's just amazing, I think, because not only have we found the inverse, but we've even checked that this is the inverse. We know the inverse is the matrix, such that when you multiply your matrix by, you get the identity matrix. And this has been successful here. And I'm very happy about that. And so I think it is also very powerful, this construction, how you reach this result and you're able to check for yourself that this result is intact and is clear. And I'm also personally happy because after 25 minutes of recording and all of these colors and all of these numbers, we're able to obtain something that's so concrete and so nice. But of course, in the exam, you don't need to check that it is the inverse matrix. If you just do this, then it is more than enough if you just proceed as follows and just say that this is the inverse matrix. This should be more than enough for this video.